We have now talked extensively about how a single agent plans, searches, and uses tools. But an important question remains. What happens when that intelligent agent invariably makes a mistake? Or what if it faces the exact same difficult problem tomorrow? In traditional AI systems, if a model fails to solve a problem today, it is guaranteed to fail in the exact same way tomorrow, unless a human software engineer manually steps in to retrain its weights or rewrite its prompt engineering code. But agentic reasoning introduces a profound and powerful new concept to solve this: self-evolution. Self-evolving agents possess the remarkable capacity to actively improve their own reasoning processes directly through their own interaction experience. They achieve this continuous improvement by leveraging two fundamental mechanisms: feedback and memory. When an agent fails executing a task, it doesn't just halt execution. It receives an evaluative signal, which is feedback, indicating that something went wrong. And crucially, it has a persistent computational substrate, which is memory, to explicitly store that interaction, analyze and figure out exactly why it failed, and adapt its future approach so it succeeds the next time. This is what researchers call continual adaptation, and it serves as the foundation for true lifelong reasoning in AI systems. This evolution happens fundamentally on two completely different timescales. First, we have what is known as intra-test time evolution. You can think of this as learning while solving. The agent adapts dynamically during the actual execution of a single task. For example, if an agent tries to parse a specific web page to find a price, but the HTML format is entirely different than it expected, it uses its internal reflection capability to correct the error on the fly. It will autonomously devise and try a different parsing strategy before ultimately returning an answer to the end user. Second, we have intertest time evolution. This is learning across tasks, representing long-term growth. If the agent discovers and confirms a highly successful new heuristic or problem-solving strategy today, it explicitly stores that finding in its persistent long-term memory. A week or a month from now, when faced with a structurally similar problem, it rapidly recalls that heuristic from memory and leverages it to solve the new problem faster, more efficiently, and more accurately. In this way, the agent's capability fundamentally persists and snowballs across thousands of different episodes. Let us look a little closer at the concept of feedback in self-evolving agents. Where exactly does this critical evaluative signal come from? Sometimes, the feedback is purely external and explicit. A web API returns a standard HTTP 404 error, a Python execution script throws an obvious syntax error trace, or the visual environment, like a rendered web page in a browser, visibly changes in response to an action. But highly capable agents can also generate sophisticated internal feedback. Through self-critique mechanisms, such as the widely used Reflexion framework, the agent essentially acts as its own harsh judge. It autonomously reviews its own historical reasoning trace, actively identifies logical leaps or hallucinatory assumptions, and generates a concrete set of textual guidelines to heavily condition its subsequent attempts on the problem. This adaptation can take several forms. It can be verbal, where the agent simply updates its internal textual instructions and prompts. It can be procedural, where the agent actually synthesizes brand new, reusable code-based tools and saves them into an executable skill library for future use. Or at the absolute bleeding edge of current research, it can be structural, where the agent autonomously rewrites its own underlying source code or prompts to discover fundamentally better reasoning algorithms. However, absolutely none of this self-evolution works without the second mechanism: memory. Memory is how an agent accumulates vital context over time. In agentic research, we break this down into three distinct types of memory architectures. First, episodic memory. This stores the highly specific, step-by-step historical logs of all past interactions and trajectories. Second, semantic memory. This extracts and stores generalized abstract facts, heuristics, and concepts logically derived from those raw episodes. Third, procedural memory. This stores the refined executable skill sets or complex tool use access patterns. Crucially, memory is not just a static relational database. An advanced agent has to actively manage it. It must intelligently decide what specific information is actually worth writing to persistent memory, how to accurately retrieve the most relevant past experiences when faced with a novel problem using vector embeddings, and how to periodically update, summarize, or heavily compress that memory so the agent's limited context window does not simply get overwhelmed with useless or redundant historical information.